Hi and welcome to the third and final part of the improved digital module. In this section, I will be outlining for you the geological framework of Krapla. Following this introduction, I will present you and discuss several examples of thermal features observed in the Krapla geothermal field. Additionally, I will provide an analysis of key soil horizons that are representative of many thermally altered areas which are surrounding the geothermal fields. The Krapla caldera is located northeast of Iceland and has a significant geothermal region which results from volcanic activity along the middle Atlantic ridge. The primary geothermal features of Krapla are located in the central eastern part of the caldera, as shown in this map. These features include hot spring fumarole and the Krapla geothermal power station, that is a geothermal site that produces up to 16 megawatts of electricity. Nearby, the Lennocourt thermal site hosts active vent and hot springs. Within the geothermal field, there are also two notable fissures or depressions, which are the VT crater and the Kveragil fissures. These fissures were created by magmatic hydrothermal eruption occurring in 1724 and in 9,000 years ago, respectively. The soil covering the geothermal areas around Krapla are predominantly made of the deposits from this eruption, along with bedrock material composed of a series of local scoria cone deposits and mostly yellow clostite deposits which were formed during subglacial eruption at Mount Krapla. Our investigation focused on these crater areas to delineate K-soil profiles, interbed variability, and alteration pattern using the methodology which was outlined in the second part of the training module. This slide shows a map of fracture system primarily oriented in the north-northeast, south-southwest, and west-northwest, east-southeast directions. These fractures are associated with area of ongoing or past thermal activity, and where we also find a series of thermal features. Some of these thermal areas developed several decades ago, includes those that were active during the Krapla fires eruption between 1975 and 1984. The map indicates a clear correlation between the location of the thermal features and the structural elements of the areas, including also some of them which are distributed around or within certain crater borders. This correlation is very similar to what has been observed at the Rotokawa geothermal field, as discussed in the previous part of the module. Starting from the thermal features around the VT crater, in particular those which are located in the northernmost part, we have basically both active thermal feature and remnants of past thermal activity. Here, the surface geology comprises erupted breccia, along with the layers of tephra and deposits from scoria cones, all overlapping or overlying yellow clostite deposits, which are mostly made of tuff beds in these craters. Our study focuses on two sampling sites, Site 1 on the edge of the altered zone and Site 2 within the highly altered region of the thermally active features. Here, fluids ascend through fractures that are located either at the perimeter of the crater or within it, and these fractures inside the crater are usually aligned west-northwest, east-southeast direction. The affected region exhibit a predominantly white to orange and reddish soil, as delineated by the dashed white line. These ascending fluids emerge through a series of aligned vents and result in the formation of fumaroles and intense alteration of the soil into clay-rich materials. This process resembles once more the acidic fluid alteration type previously discussed in the first two parts of this module. The thermally unusual ground was also identified using a portable thermal camera, which is a valuable tool in geothermal environments. While the accuracy for temperature readings is the best when up close at a distance of 1.5 meter, the use of this camera can be still of use because you can detect anomalies on both large scales and in a close-up situation. For instance, in this case, it revealed a significant altered area from afar and close-up details of sulfur-filled cracks, which can reach temperature up to 65 degrees Celsius. It also shows that the zoning around the very hot fumarole, where the temperature at the fumarole vent can reach 97 degrees Celsius. And also appeared from the use of this camera that temperature decreased quite rapidly away from these cracks and fumarole in the ground. At Site 1, the soils appear mostly cold and in sort of unaltered state, but warm up significantly in the white altered portion, reaching temperature around 20 degrees C. The site offers an ideal location to study the variability within soil layers and to assess how basically the alteration affects them. As already mentioned before, in this area we primarily deal with soils which are composed of yellow clostite tuff material, consisting predominantly of brown sandy material with minor pepplicides component in its original or unaltered state. Temperature increased gradually from approximately 10.7 to 16.3 and 24.1, moving from the colder to warmer regions or portions. At the same time, changes in soil texture and composition were observed through the sample cylinders used for soil permeability measurements. In particular, sample 4 fractured during the measurement process, so necessitated a collection of an additional sample labeled sample 9. At Site 2, the upper layers of soil retain similar characteristics to those observed at Site 1, as exemplified by sample 8. However, deeper layers show increased alteration. As well, temperature varies across this layer, ranging from the 14.8 in the colder superficial region to 23.8 to 57.8 to 82.9 Celsius, deeper in the ground and in the more altered areas. The texture analysis indicate that samples from 5 to 7 from Site 2 exhibit more degradation and clay content compared to sample 1 from Site 1, which also underwent similar alteration. Then, component analyses were conducted in the lab using optical and scanning electron microscopes, with example of key class shown here on the side. These analyses were crucial for identifying minerals, distinguish different soils, and estimating their relative degree of alteration. Here, this histogram, for example, showed the component percentage in the different soil samples, with sample 1 and 7 being rich in altered clast. The figure on the right presents 4 plots illustrating the properties of all the collected samples. It shows how permeability varies across samples in relation to humidity, compressive strength, and shear strength. To bear in mind that permeability value, the highest one of about 5 per 10 to the minus 13 square meters, correspond to the higher value of instrumental threshold of the soil permeability. The data indicates that there are distinct patterns. Unaltered or slightly altered soil, like for example sample 8 and 9, have low permeability, moderate humidity, and moderate strength. Moderately altered soil, like sample 6, which is the one overlying the hot and dark soil 7, show the lowest permeability, dry condition, and relatively low strength. And in the end, highly altered soil, like sample 1 and 7, they exhibit very high permeability, different degree of humidity or moisture, and in general low strength. So combining this data with geological and structural information allow us to sketch the condition at Site 1 and 2. Here, yellow clostite units are intersected by a series of fractures which create dome-shaped pattern of alterations as fluids ascend. The most intense alteration occur near to the fractures, gradually decreasing farther away. Surface temperatures near the fractures can exceed 80 degrees Celsius and can reach over 95 degrees directly at the fracture and the fumarole spots. The thermal anomaly declines rapidly to about 20 degrees Celsius away from the fracture. Unaltered to slightly altered soil are generally very stiff, but the intense alteration significantly reduce the strength, increasing the permeability. Indeed, most of the white soils in the thermal area are very soft and unstable due to this alteration. Increasingly, the deeper and less permeable soil appear also to act as a sort of like a cap layer, which can reduce or buffer the temperature flow and potentially limiting the fluid movement upwards. Surface exposed, highly altered zone can appear dry, close to the vents of the fractures, while those which are like below the ground and covered by less permeable layers appear to retain the hotter state and the moist. Now I will present additional example of soil found east of the T crater. These soils form within yellow-classite sequence in both tuff and pillow-breccia layers. The surface material appears whitish to beige color due to the intense alteration process. Although the ongoing thermal activity is not observed in the crater flank, where sample 1 to 6 were collected, the base of the crater exhibits slight warm condition with soil temperature measuring about 18.4 degrees Celsius. At the transition zone, there is a change in the soil composition. Sample 1 consists of less altered tuff with pumiceous clasts, whereas sample 2 and 3 show slightly more alteration. The color shifts from reddish brown to light brown and orange, indicative of increased state of alteration. Additionally, the pumiceous fragments show signs of degradation. The extent of changes due to alteration increases significantly from sample 4 to sample 7. The colors shift towards shades of purple-gray, bright purple, with white fragments in sample 4 and 5, and light and dark gray in sample 6 and 7. Neither sample shows any pumice-like texture. Sample 6 in particular contains a substantial amount of clay and appears to be moist, whereas sample 7, which is warmer, is more granular and dry. Here we present similar graphs as before. It is noteworthy how both permeability and strength decreases significantly when moving from the outer hollow zone to the intensely altered zone within it. Sample 6 is confirmed to be the wettest, and along with sample 5 and 7, they form a cluster characterized by low permeability and very soft soils. In contrast, sample 1 to sample 4 are much stiffer and relatively more permeable. And it is very interesting that sample 5 and 6 are located in the detachment area of a small landslide that affected the inner part of the crater. And this is justified by their low strength, and which also emphasizes the importance of characterizing the soil to understand the distribution of thermal feature. Specifically, this very soft and weak material facilitate the occurrence of mass movement in this particular case. We now move in the southern part of the Kveragil fissure. In this region, there are numerous areas which exhibit evidence of past and current geothermal activity. The surface here are mainly consist of deposits from the Kveragil eruption, which are primarily layers of pyroclastic flow deposit as depicted in the images. Our investigation focuses on two specific locations named Kveragil South 1 and 2. The first location is an area apparently without the presence of any thermal feature, while the second is situated in an area that has been altered by ongoing thermal activity and is located close to other thermal features. At Kveragil South 1, within one eroded channel, the outcropping deposit consists of alternating ash-rich and lapilli-rich layers. Soil temperatures were consistently higher than the surrounding air, ranging from approximately 12 to 25 degrees C, indicating some thermal activity at depth. Both types of layer exhibit permeabilities which go between 4 to the minus 14 up to 1 per 10 to the minus 13 square meter, and are relatively dry with moisture content peaking at around 40%. In terms of strength, both compressive and shear strength are concentrated around values of 1 to 2 kg per square centimeter, indicating that soils are firm and stiff. Variability in these values primarily reflect differences in textures between ash and lapilli dominated layers. At Veragil South 2, we studied two additional soil profiles. One was the unaltered and relatively warm with temperature gradient similar to the one observed at Veragil South 1. The other was highly altered, close to the main thermal feature and with a hotter temperature gradient, which temperature increased from 27 degrees C up to 74.2. These sites were about 30 meters apart. Permeability for samples 6 and 11 could not be measured because sample broke during the operations. Most of the soil had permeability above 1 per 10 to the minus 13 square meters, except for soil 5 and soil 9, which appear to be at a similar depth within the soil profile. Humidity of the soil at site 1 were relatively lower, while soil samples had strength values below 1.2 kg per square centimeter, indicating they were soft to very soft, with the colder profile sample having relatively higher strength values. Comparing this profile and Kveragil South 1 shows significant changes in the property, which are mostly due to the alteration effect. Here we compare the data using the plots of Kveragil South 1 and 2, and the difference between them became more apparent. In addition, there is a conceptual model below, where we can observe that the soil profile at South 1 and South 2 were eventually located at different distances from fracture in the yellow clastite. These fractures enable the movement of hot fluids to the shallower layer of the Kveragil pyroclastic density current deposit. At Kveragil South 1, the sampled soils they show lower permeability and relatively higher strength of the ash and lapilli-rich layers compared to those which are at South 2 profiles. At Kveragil South 2, in particular Site 1, which appear very similar in texture and appearance to the layer present at Kveragil South 1, many samples they show higher permeability with only one subsoil layer that exhibit the lowest measured permeability, although this does not appear to buffer or affect the thermal gradient. It is important to know that changes in permeability that we measure are within one order of magnitude, as shown in the plots. However, the proximity to hotter feature might cause significant changes even tens of meters away from the fractures. This also suggests that at Kveragil South 1, there might have been a source of fluid, but probably at depth, as no surface manifestation were found in the area. Need to be noticed that this observation should be considered preliminary, but they demonstrate how quantifying key soil parameters and conducting laboratory analysis can help us understanding the nature of thermal features and their relationship with local structures and hazards like landslide and unstable grounds. To conclude this training module, I would like to emphasize once more that geothermal manifestations are manifold and exhibit significant variability at different spatial scales. Changes in pressure and temperature, as we saw, can cause a wide range of physical characteristics and response of hydrothermal aquifer. By mapping the physical, mechanical, and thermal properties of soils in geothermal areas, we can better understand how surface thermal features can develop, evolve, and how they are distributed. This mapping also helps to identify the hazards related to soil alteration processes. And finally, field results can be used to create models that better help to assess critical or disruptive processes within geothermal environments. This concludes the third section of the digital training model, geothermal environments, where we discuss examples from the Krapla geothermal area. Below you will find the referenced literature and additional readings that can provide a deeper understanding of the Krapla geothermal region. So thank you all for staying with me throughout this training module. I really hope it expanded your understanding of intricacies and complexities of geothermal environments and of course of their associated hazards. I wish you best of luck as you navigate challenges in the geothermal world.